So we've got a whole bunch of trees we have to look at, Michael, and we're going to have come up with some clever way to look through them. And this gets us back to something that we've talked about before, which is the notion of bias, and in particular, the notion of inductive bias. Now, just as a quick refresher, I want to remind you that there's two kinds of biases that we worry about when we think about algorithms that are searching through space. One is what's called a restriction bias, and the other is called preference bias. So a restriction bias is nothing more than the hypothesis set that you actually care about. So in this case with decision trees, the hypothesis set is all possible decision trees. Okay? That means we're not considering y equals 2x plus 3. We're not considering quadratic equations. We're not considering non-Boolean functions of a certain type. We're only considering decision trees and all that they can represent and nothing else. Okay? So that's already a restriction bias. And it's important because instead of looking at the infinite number, uncountably infinite number of functions that are out there that we might consider, we're only going to consider those that can be represented by a decision tree over in all the cases we've given so far, discrete variables. But a preference bias is something that's just as important, and it tells us what sorts of hypotheses from this hypothesis set we prefer. And that is really at the heart of inductive bias. So Michael, given that, what would you say is the inductive bias of the ID3 algorithm? That is, given a whole bunch of decision trees, which decision trees would ID3 prefer over others?
So it definitely tries, since it's making its decisions top down, it's going to be more likely to produce a tree that has basically good splits near the top than a tree that has bad splits at the top, even if the two trees can represent the same function.
Good point. So good splits near the top. Right? And you said something very important there, Michael. Given two decision trees that are both correct, they both represent the function that we might care about, it would prefer the one that had the better split near the top. Okay. So any other preferences, any other inductive bias on the ID3 algorithm?
It prefers ones that model the data better to ones that model the data worse.
Right. So this is the one that people often forget. It prefers correct ones to incorrect ones. So given a tree that has very good splits at the top but produces the wrong answer, it will not take that one over one that doesn't have as good splits at the top but does give you the correct answer. So those are really the two main things that are the inductive bias for ID3. Although when you put those two together, and particularly when you look at the first one, there's sort of a third one that comes out as well, which is ID3 algorithm tends to prefer shorter trees to longer trees. Now that preference for shorter trees actually comes naturally from the fact that you're doing good splits at the top. Because you're going to take trees that actually separate the data well by labels, you're going to tend to come to the answer faster than you would if you didn't do that. So if you go back to the example that we went before, where one of the attributes doesn't split the data at all, that is not something that ID3 would go for, and it would in fact create a longer and unnecessarily longer tree. So it tends to prefer shorter trees over longer trees, so long as they're correct and they give you good splits near the top of the tree.